Welcome to the Python Meetup and welcome to FusionBox. So I'm just going to introduce today's talk, which is by Alex, who will be talking about concurrent programming in Python with async and await. So enjoy the pizza, enjoy the beer, feel free to take more, and Alex, the floor is yours.
Thanks, guys. So yeah, Ian said, like he said, I'm going to be talking about concurrent programming with async and await in Python. This is just going to be like a really brief overview of what's possible, because we try to keep these talks short so you guys can interact with each other more, and long talks are really boring. But I'm not even going to be able to cover half of what's possible. So I kind of want you guys to leave the talk like half confused and half curious, because not everything's going to make sense. And also, if you're newer to Python, I'm going to be going over some things that you might not understand. If you have questions, remember them or write them down. Ask me afterward. I'll be happy to explain anything that you might have missed. All right, so let's talk a little bit about concurrency and asynchronicity. The first thing I want to say is that concurrency is not parallelism. So there's a difference between running code on, running only one routine at a time, but being able to switch in and out of running different routines, different coroutines, and then actually running multiple computations at the same time. Concurrency is when you're running one thing, but you can swap out and you don't, two operations can overlap in time. Parallelism, you can run two operations and they're actually executing at the same time. A major use case for concurrent programming is network programming. It works well because you've got one server and you've got many clients, and they're not always communicating. There's some sort of delay, intermittence, so you can handle requests as they come in, but you have to be able to have multiple connections open and things like that. So Python 3.5 introduced the keywords await and async. And they really changed the landscape of asynchronous Python. So it's been possible to write asynchronous Python for a really long time, but it's also been hard. We've had past frameworks like Twisted and G-Event, and recently as Python 3.4, we've got Async IO. But I remember using Twisted like 5 years ago, and it was just a massive pain. I don't remember anything about it anymore. Maybe it's gotten better, but it was just really awful. So you don't really need to know about any of these. You might need to know a little bit about Async IO, but await and async really simplify the concurrent programming landscape. So let's take a look at some code. We have here a server. This is the simplest server that you can possibly write. I hope everybody can see that. I can increase the... Yeah, is that better? Okay, so we've got a server. This server opens a socket on a port, and it listens for incoming connections. And then when a client connects, we have this handle client function, which down here basically will print that we got a connection. We read data in from the network, and then we just send the data back out, right? So let's run this. So I'll connect to a local port here, and we've got a connection, right? So I can send test data, and we get test data back, and I can send more data, and we get more data back. The problem is, if I want to open a second connection, first of all, you see that the server doesn't even acknowledge the second connection. On the left there, there's no connection from. And if I send test data here, we get nothing back, because the server is dedicating all of its time to the first client, and it's not switching across all of the different connections. So once we close this, then they can handle a second client and more data, and it's responsive again. This is a really not a very useful server if it can only have one client, right? So how might you change this? You could use threads. Here we go. Whoops. So this is almost the same server, but it's using threads. So right here, we see that every time a client connects, we're spawning a thread, and we're making the thread run the handle client, and it'll run until the client closes. So if we kill these, and we kill the server, and we run the thread echo, we'll see I can connect, I can type test data, and I'll get test data, and I can connect here, and I can also send test data and get back test data. So this is slightly a more useful server. The problem is that spawning a thread for every connection is not really very efficient. And I'll talk about that more in a little bit. So this is the async example. Make that a little bit bigger. It looks almost exactly like everything else, except it's got this weird async def here. That it wouldn't be valid in Python earlier than 3.5. And we've also got these weird await statements. So this will run pretty much exactly like the thread example. We've also got this weird run thing here, which I'll talk about in a minute. But it'll run exactly like the thread example. Python. I mean, I don't really have to demonstrate this. I think you guys get it. Test data. And both of these, you can handle both of them at the same time. So that's sort of the idea behind asynchronous. You can have these asynchronous statements, asynchronous functions called coroutines, and you have this await keyword that is used to call other asynchronous coroutines. So what's going on here exactly? When you define a function with async def, that makes it a coroutine. It makes it something special in Python. It's not a normal function. And coroutines are just methods that you can interrupt, or that can be interrupted by the interpreter to do other things. Whatever that other things, it doesn't really matter. You can run many coroutines at the same time. And it's basically, you get essentially the same behavior with threads and subprocesses, but you have different trade-offs, which I'll talk about also in a minute. So how do you write asynchronous code? There's kind of a few simple rules. Every coroutine has to be defined with async def, and you can only use the await statement inside a coroutine. If you use await outside of a coroutine, that's going to be a syntax error. And coroutines can't run on their own. Something has to run them. And I'll talk about that in a little bit more as well. The other thing, I'm repeating myself there. Sorry. So async def marks the function as a coroutine, and only coroutines can be awaited. You can't await a regular function inside a coroutine, but you have to await a coroutine because otherwise it won't run. So we're talking about these functions that can run themselves. What runs these functions? The event loop does. It runs one loop at a time, one coroutine at a time. And when a coroutine halts, the event loop has a list of all the other coroutines that are ready to run. And it checks if any of those are ready to run. And if they are, then it starts running one of them. And it'll run it until the coroutine halts or finishes. And then and then it goes back to one and checks if any other coroutines are ready to run. So this is really the main part of the talk. I want to finish up with advantages and disadvantages of asynchronous code. The biggest thing is that asynchronous code doesn't allocate nearly as many resources as threads and processes. So when you're running asynchronous code, you can have thousands and thousands of coroutines running at the same time for relatively little memory usage. Whereas with threads, if you spawn a thread for every single client, and you have thousands of clients at a time, you're going to be ballooning in memory, because every thread has to have its own stack and its own frame and keeps track of all sorts of different things, and they take time to start. Same with processes. When you start a sub-process, you're forking the entire Python interpreter. So if you have eight Python interpreters running, that's going to take some memory. Coroutines don't have any of those disadvantages. And the other thing, the coroutine can choose when it's interrupted. So I have this example of basically adding several numbers together. So if we go, I have this multi-thread increment code. And what this is doing is it's going to increment a counter. We start with a counter that is set to 0, and we have a function that increments the counter 1,000,000 times. And we want to run this concurrently. So we're going to start 2 threads. I realize pointing at the screen doesn't actually help. We've got 2 threads that are going to both be running this code at the same time. And this is still concurrent. This is not parallel because you have the global interpreter lock in Python. So only one thread is running at a time. We're going to start these threads, and then we're going to wait for them to finish, and then we're going to print the counter. If you know about concurrent programming, you know what this point is. If you don't, you may be surprised. We should expect to see 2 million pop out, right? We don't. And what's more, every time I run this, the answer is going to be different. Can you guys all see that? Yeah? I can keep running this, and it'll be a different number every time. And that's because adding 1 to a counter is not an atomic operation. It's 3 operations in Python. And a thread can stop executing in the middle of adding 1 to a number. So you load a number. The Python loads a number into its register, and that's one operation. So it can be interrupted after it's loaded. Then it adds 1, and then it has to store the variable back into main memory. So that's 3 places where the thread can just stop and the other thread can go. So if you load 5 and then get interrupted, and the other thread loads 5, and you add 1, and the other thread adds 1, and then the first thread resumes and adds 1, you're going to get 6, even though you've incremented twice. This is kind of, if you're not familiar with this, I'm happy to talk about this more in depth personally, but it's sort of weird. So it'll always be lower than 2 million, is the point. When you have the async increment, oh boy, we have more or less the same thing, but we've got this async def as usual. And we have this await sleep 0. This is just sort of a hack that I put in to make sure that after every increment, the coroutine gets interrupted. So I'm choosing here to be interrupted. Normally, there's nothing really here to wait for. There's no network connection or anything. This is a contrived example. But if we run this, first of all, it's going to take a lot longer because it's being interrupted after every single increment. Whereas the multi-thread, you can add 100 and then it'll switch and add 100 somewhere else, and then about 100, not exactly. So this is taking a lot longer, but you get 2 million. It's correct, which is important in code. A couple of disadvantages. It takes a lot of effort to program asynchronously because you have to maintain asynchronicity all the way down to whatever pauses you have in your program, to whatever blocks you have. If you need to read from disk, that needs to be asynchronous. If you accidentally introduce a 5 millisecond delay in your asynchronous code, other coroutines can't run while you're waiting for data to be fetched from disk or from the network. So you have to really keep it in mind. And it's not parallel. So you're still restricted to one thread, one process, and you've still got the global interpreter lock. And I'll talk about how you can get interrupted here. I have this function, so thread sleep here. This is the same server that we're all used to by now, except it's slightly different because what happens is If I send the server a number, it'll sleep for that number of seconds. So we can go back here, if I type properly, and run. And now we can connect again, and I'll send it, 1 second. So it sleeps for 1 second, and then it sends back 1. Right? I can do this. I can 2. It'll sleep with 2 seconds. But the important thing is that I can connect on both of these. This is using threads, remember, and I can sleep on both of these, and it'll still keep working. I can even set this one. Nope. Let's start that over. I can set this one to sleep for 10 seconds, and this one will still be responsive, right? I'm still getting 2 seconds back, 2 seconds. Even though this one stopped, it's sleeping for 10 seconds before it returns, I'm still responsive on my other connections. You can see where this is going, probably. If I go to asynchronous sleep here, this is the same code. It's asynchronous, and it's not using threads. So here we're sleeping for the sleep time, and we're sending the data back. It's the same thing, just with, it's the same thing with threads, with asynchronous connections as opposed to threads. So if we go back and we connect again, it works much the same way. You connect, and you can send stuff. But this time, the server is only able to run one of these at a time, and it's any sleep is going to interrupt the other program. So if I type 10 here, I can type 1 here, and nothing's going to happen until the first one stops. So the difference between the two is in threads, the interpreter is choosing when to switch back and forth between processes. This is going back to the advantage I was describing. You choose when the task switches. You also, sometimes you choose wrong if you make a mistake. The Python interpreter, when it's running threads, it chooses when to switch back and forth. So if a thread's asleep for 10 seconds, it says, okay, that thread's asleep. I can switch over somewhere else and run some other code while this thread is sleeping. With this, you have to be the one to tell Python where to switch. So it's an advantage and a disadvantage. So that's kind of my talk. I've really only scratched the surface of async, and I see a lot of confused faces, which is kind of good and kind of bad. But I think I've succeeded. There's a lot more stuff that I didn't cover. You can use asynchronous context managers, like async with, and asynchronous iteration. That should be async for. I use the Curio library in a lot of these. This is a really cool library to check out if you want to play with asynchronous code. It's written by David Beasley, who is a pretty widely known Python talk. He gives a lot of Python talks. I think he might be a core developer. And there's a 1 hour long talk that he gives called Fear and Awaiting in Async. And he talks for an hour about this stuff, and he goes into really good detail about what is going on behind the scenes. He shows you what really weird and probably bad things you can do with async. So if you're curious about this, I definitely recommend watching that video. Yeah, and that's all I have for you guys. I'm going to turn it over for questions now. Yeah, sure, go ahead.
My name is Nick. I actually wrote my first Python script today.
Yeah?
My buddy Dan invited me over.
Awesome.
So I learned Ruby, and I wrote a script to consume API that I built Ruby, and that's my experience. But I'm questioning, you made a very clear statement that if you're going to use async, you need to be consistent.
Mm-hmm.
You need to use it all the way through.
Yeah.
And then you displayed how async would interrupt threads. Like how, if you have an async call going out to Python and it's doing some work, then if you want to do another action somewhere else, you're going to have to wait for it. How do you, so if I'm going to write a program in Python that is utilizing these tools, do I have to make that determination right at the start? If I'm going to use async as part of my program, is there no other way that I can like, I don't know, use multi-threading as a way to calculate? I guess I'm not exactly sure what I'm trying to say. But to me, it seems like you're splitting the two apart. You either use async or you don't, and that's the choice you have to make from the get-go.
I think that's probably true. I haven't written huge asynchronous libraries. This is something that is new in Python and that I've been kind of interested in playing around with. So I don't have a huge amount of experience with it. But yeah, it is something that you need to decide. All right, we're going to do this asynchronously, rather than we're going to use threads or multiprocessing, just because it takes you have to. Your entire code base has to be async friendly, basically. So you start from the beginning. Any other questions? Yeah.
What's your favorite problem you solved with using
The toy server that I showed you. I've been playing around with it for like about 2 weeks now. I think it's cool, and I wanted to share it with you guys. I don't actually use it in my day-to-day work.
Do you see a use case for it?
Yeah, for like I said, network programming is going to be a huge one. There might be other situations. Anytime where you're waiting on some sort of input-output, anytime when there's a clear distinction between when Python is doing work and when Python is waiting. And when Python is waiting, you can use async to make Python do other work while it's waiting for the data that it needs to continue its computation in the first coroutine. Yes?
Do you suppose if you get rid of the local interpreter logs, you're using Python, and you're going into asynchronous programming, do you think multiple threads are going to pick up the coroutines?
There are libraries for sharing coroutines. You can have an event loop that knows about multiple threads and can dispatch coroutines to multiple threads. You can also do it in Python with multi-threading. You can start, if you have 8 CPU cores, you can start 8 processes and distribute the coroutines between your 8 processes, and then you're using multi-threading. You're using concurrency and parallelism. So yeah. Curio has stuff, I know, that has a really nice API. Async.io, also, the library, has methods for dealing with multiple threads, multiple processes, sharing between the two. Anybody else?
Do you like it?
I do. I think it's awesome. But I don't have much experience, so I think it's a fun toy. Can you write anything useful with it? I think it's a little bit too early to tell. Yes?
Is it better than promises in Node.js?
Do you want, yes?
It's the same thing.
I don't know too much about promises, so I think they're slightly different, but it might also be almost exactly the same. I know, Gavin, do you know if they're exactly the same?
It's a really similar concept, but the ergonomics are way better in Python.
Awesome.
The backend guys.
Yeah. Okay, anybody else? All right, thanks, guys.